Okay, so we're very happy to have today Paul Biran from ETH, who will talk to us about persistence and triangulation in Lagrangian topology. So go ahead.
Thanks for the invitation. You hear me and see everything? I hope.
Yes, all good.
Okay, so what is the goal of this talk? So, well, we all know that there are triangulated categories that play an important role in symplectic topology, like the derived Foucault category, in algebraic geometry too, category of coherent sheaves. And in red here, you see another theory. It's the theory of persistence models that comes from applied topology, from topological data science, and has found many applications, successful applications in symplectic topology, in Hamiltonian dynamics. And the goal of this talk is try to put the two structures to work together and create something which is called triangulated persistence category, TPC. And the goal of this talk is basically to show how to do this. Now, the talk is based on joint work with Octave Cornea and Jun Zhang. I think about a month or two ago, Jun gave a talk in this seminar about it. And I definitely don't intend to reproduce the same thing. So this talk will concentrate really on the underlying ideas. So it's going to be a very intuitive talk, and I try to explain how geometric intuition tells us what to do in the algebra, how to set up the algebra. And hopefully the algebra will tell us one day something new about geometry. So this is a work in progress. And this brings to mind a saying attributed to Vladimir Arnold when he was asked what is the difference between applied mathematicians and pure mathematicians. He said that applied mathematicians are paid by the result. Pure mathematicians are paid for the process of arriving to the result. So I heard this story from Yasha Eliashberg, so it's not firsthand. So in this talk, I'll be pure mathematician indeed. Okay, so let's recall some algebra. So we have persistence models that most of you know very well. So these are just a directed system of vector spaces and with maps that go from, so the vector spaces are indexed by the real numbers, and we have linear maps that go from vector space S to vector space T when S is smaller or equal than T, and they are related one to the other. They are compatible with compositions and so on. And usually in persistence homology, you impose more conditions like finite spectrum and some left continuity with respect to time. And this works very well in our setting, but I'm going to ignore them in this talk because they'll be not so relevant. A piece of notation here, I'm going to denote V smaller equal S for VS many times. That's my personal preference. So a typical example is if you take a filter chain complex, the filtration being indexed by the real numbers and being increasing, like you see here. And you can also take the homologies of the subcomplexes, and this gives you a structure of persistence model with maps between one homology and another one induced by the inclusions. Right, and of course, these things appear in geometry. If you take a Morse function on a manifold, then you look at the Morse complex of sub-level sets here, you will get, and the homology of this, you will get a persistence model. It appears in Lagrangian floor homology and also in Hamiltonian, closed loops floor homology or fixed point floor homology. And just to mention, well, all these persistence models have very interesting invariants like barcodes, There are interesting measurements you can do with them, like all sorts of distances between sets of barcodes, bottleneck distance, interleaving distance between persistence modules, and so on. Okay, so let's go to category theory. So what is a persistence category? So it's a category, and the homes between objects are persistence modules. So home between two objects is a persistence module. And you know, categorically, I really need to specify a set for the homes. So in reality, the set is going to be taking all those, you know, levels of the persistence together and labeling a map here with the level of the filtration to which it belongs. Okay, so this means that I'm losing linearity here because I cannot take an element f comma s and add it to an element g comma t if s is not equal to t. All I can do is push them to the future to some level which is bigger or equal than s and t, and then I can add them. And another axiom here is that the composition in the category is compatible with the persistence. So structure, so when you take a morphism here and a morphism here and you compose them, you land in a morphism that is labeled by filtration level not more than R plus S. The identity is by definition in level 0. Every persistence category comes together with two associated categories. One of them will denote C0. This is, it has the same object as C, but the morphisms are just taken to be morphisms where the filtration is not more than 0. And C infinity is just the total thing. You just take the direct limit where the filtration level becomes higher and higher, and you take the lim of these homes. Important to keep in mind, none of these categories is a persistence category. These are honest to go categories. These are categories without, without this additional structure. Right. Here's a couple of examples. Well, the simplest one is you take the filtered chain complexes and the home at level R. So we are here now between two such things. Maybe it's better. This is maybe too fat. The homes between two such things are just linear maps between the chain complexes that shift. I'm gonna, by slang, call this level of filtration sometimes action, because we have in mind action from symplectic topology. So these are just linear maps that shift action by not more than this number R here, okay? You can also take the homological category of the category in 1, or maybe I should say the persistence homological category. So you have the same objects, filter chain complexes, but now the home smaller or equal than R is just the homology of the chain complex, home smaller or equal than R. And what does this calculate for you? These are just chain maps up to homotopy that shift filtration by not more than R. You can look at filtered DG categories or even filtered A infinity categories and take their homological category. In the DG category, these are honest categories. So the underlying chain level is already a persistence category. In the A infinity category, you really need to go to homology to get a persistence category. Okay, so let's quickly say something. Well, there is something called persistent functors. So these are just functors that preserve the persistence structures. Important to note that if you look at the definition, you see it doesn't make much sense to allow them to shift filtrations, the way they act on homes, on morphisms. And there is also persistence natural transformations between two such functors. between two such persistence functors, those are already allowed to shift filtrations. Okay, so if you take all those functors together and form a category out of them where the morphisms are persistence natural transformations, you get a persistence category again. And now we get to a very important point, and this is shift functors. So what is a shift functor? So a shift functor is actually not one functor, it is a family of functors, sigma r, parameterized by the real numbers. And well, these functors are, they satisfy this rule that when you shift by S and then by R, it's the same as shifting by R plus S. Shifting by 0 is the identity. But these functors, they don't come alone. They come also with a family of natural transformations between any two such functors. They are denoted here by eta rs. These natural transformations, they shift action by s minus r. And therefore, if you unwrap these definitions, you will see that home between the shifted object A and any object, the home with action not more than s is the same as the home of action not more than r plus s, a comma x. Formally, you don't have an equality here. There's a natural transformation, one of those etas that will take care of an isomorphism here. But I was a bit sloppy about this here. So you have this shift functor. So a typical example would be that you take a filter chain complex and you just shift the action like it's written here. It's quite obvious. Now comes something which is a bit subtle. So let's fix an object, and then let's look at the natural transformation associated to the object A. So this gives us a morphism between the shift of A and A. I took R and 0 here. So we are here. So this morphism, where does it lie? It lies in the homes between the shift of A and A, but the morphisms that shift action by not more than minus R. And now you can take this thing and push it to the future. You push it to 0, as you see here. You push it to 0, and you land in a morphism from the shift of A to A that shifts by not more than 0. And this morphism is going to be very important in all sorts of places in the talk. Oh, sorry, I erased things. And we denote it eta R. So just an example, what is eta R in this case of filter chain complexes? Well, it's just taking a chain complex, shifting it backward, and looking at the inclusion into the original chain complex, like you see here. Okay. And now comes another important definition. Suppose you have a persistence category endowed already with a shift functor. You take an object and a non-negative R. We will say that that A is R acyclic if when you take this morphism, like sending A to its forward shift, you get 0. This turns out to be equivalent to requiring that when you take the identity on A and push it R units to the future, you get 0. And here is another equivalent condition. So again, a typical example that many of you, I'm sure, know is you take an acyclic filter chain complex. So it's acyclic as a chain complex, but it is also filtered. And then to this, you can associate something which is called the boundary depth. And if the boundary depth is R, what you will get in the persistence homological category of filter chain complexes is an R acyclic object. So R acyclic objects are going to be important very soon. Let's go on here. Okay, now we have to go very quickly over the second ingredient. This is triangulated categories. Again, I'm sure that most of this is well known to most of you, but just for the record, so we have an additive category. This means that we can form direct sums in it. And it comes also with a translation functor, T. So do not confuse this translation functor with our shift functors from before. This T is shifting degrees, not action. And I'm gonna really ignore it for most of the talk, although it should really be there. So you have these two things, and wait a second, something is not function. Now it functions. Right, so you have such a category together with a collection of diagrams, which are called distinguished or exact triangles, and they satisfy a list of axioms. So let's to motivate the subject, at least historically, these triangles are generalizations of what we know from topology and algebra as mapping cones. So if you have a chain map between two chain complexes here, you can form a new chain complex, which is called the cone of F. So it's a direct sum of A with degree translated and B, and it has this differential that you see here. And okay, it fits in some diagram. A goes to B, and then B is included in the cone, and then you have a projection back to A. And this diagram is a prototype of what you would call a distinguished or an exact triangle in a triangulated category. So here are the axioms. Axiom number one is that every map from an object A to an object B can be completed into a triangle that is in the distinguished class. You know, the identity from A to A and then to 0 is a distinguished triangle. If you have an exact triangle and you have another triangle which is isomorphic to it, so isomorphism of triangles is straightforward, is exactly the intuitive thing that you think it is, then the isomorphic one is also exact. So this is first set of axioms. Second set of axioms is about rotation. So if you have a triangle that belongs to the distinguished class, then like this one here, then you can rotate it and get a new one. And the new one will also be exact or distinguished. So this is a rotation axiom. Third axiom is that if you have one exact triangle and another one, and you have maps from A to A prime, from B to B prime, then you can complete this diagram, these two maps to a diagram between triangles. The completion need not be unique, it just needs to exist. And okay, now we get to something which is called the octahedral axiom, which is in full generality a bit awkward to draw and explain. So I don't know, it's kind of thing that you don't do in public. What I show you here is a partial case of it. So this is not the full axiom. So the octahedral axiom really addresses the following question. So suppose you have a map from A to B, like here, and another map from B to G. Then you can compose them and get a map from A to C that you see here. You can also do something else. You can go from C to L. Sorry, I forgot to say. So let's complete the first map into a triangle, ABK, and the second one, BGL. Now you can go from C to L and from L to B. Sorry, you can go from L to B and then from B to K, and then you get a map from L to K, which is the map here, right? And the octahedral axiom basically says that if you take the mapping cone of G composed F or the mapping cone of K composed L, you get the same object or isomorphic objects. So it's depicted here as cone G composed F is the same as cone of a map between the cone of G and the cone of F. And the map is really this K composed L that you see here. So that's the octahedral axiom. And I want to remind another important thing about triangulated structures. And this is that if you fix an object, any object, and you take an exact triangle like that, then Holmes home x comma variable and home variable comma x. So you have here two functors, one covariant, the other contravariant. These two functors are exact. So this means that if you take a distinguished triangle, you're going to get an exact sequence. So here I did it just for the first functor. Okay, so both of them are exact. This is not an axiom. This is a statement that you can prove, and it comes from the axioms. Of course, this put together with the with the rotation axiom means that you will actually get long exact sequences, right? Because you can rotate and apply the same principle again. Okay, let's move on. And now let's put the two structures together. And I think this appeared already in the talk that June gave. So let's start with the persistence category endowed with a shift functor. And we would like now to define what does it mean to have a triangulated structure on such a persistence category. So there are three things that we need. First of all, we need to have on C0, which is, we view it like a base category. It's the same object as C, but the morphisms are those that do not shift action. This should be a triangulated category given in advance. Second thing is, well, the last thing that I showed about the homes being exact functors, we want them to continue to be exact, but now with the filtrations. So when we apply home not more than R, you get exact functors, but on what? These are exact functors on C0, right? So C0 is where you have a triangulated structure. And the third one is that if you fix a non-negative action, R, and an object, then remember this morphism eta R, which was basically including the shift of A inside A. So when you take the cone of this, or put differently, when you complete this into a distinguished triangle, you get here an acyclic object. Not just an acyclic object, it should be R acyclic, okay? And a little exercise, indeed, if you take this chain complex and include it inside, so you take A and shift it back by R, and take the inclusion and take the mapping cone of this, is a few lines of calculation show that the boundary depth of this is R. So this is an acyclic chain complex and its boundary depth is R. So these are the axioms, and let's say a few more things in the same direction. These axioms give us the following important notion, and it's a notion of an R isomorphism. So an R isomorphism is not really an isomorphism. An R isomorphism is the following thing. So if you have a map in the category C0, so the map F should not shift filtration. It's called an R isomorphism if you can put it inside an exact triangle like that, where the third object here is R acyclic, okay? So we all know that, saying in a triangulated category, saying that a map is an isomorphism is the same as saying that the cone or the object that comes after completing into a distinguished triangle is zero. So here it is an attempt to imitate that, but with a weight, with taking into account the filtration. So this is the definition. And then when you check a little bit the properties, you see that R isomorphisms always have weak inverses. So there are maps like G prime from B to the positive shift of A and G double prime from the negative shift of B to A, such that when you compose them here and here, well, you don't get the identity, you just get these inclusion maps eta R, okay? And maybe, yeah, so here what I did here, I will not spend time on this here, but what you see here is just, oh, sorry, I erased many things, is explaining what is an R isomorphism for filtered chain complexes. So these are just maps that have a homotopy inverse, but the chain homotopy required to take you from the composition of G and F to the identity shifts filtration by not more than R. So that's a typical R isomorphism. Okay, and this brings us to the central object for today, and this is the notion of weighted triangles. So again, we fix a non-negative action, R, and we look at a diagram that looks like that. It's a map from A to B, from B to C, and then to the shift of A by, okay, minus R here. And this is a diagram that lives in C0. So these maps do not shift action. You can always arrive to this situation by shifting objects. And we say that this is an exact triangle of weight R if the following holds. So you should have a twin triangle to this triangle in C0, which is really exact, but it's not really it's not really an isomorphic triangle. It's an R isomorphic triangle. So you should have a C prime, another object C prime here, that enters into an exact triangle A, B, C prime, A. Secretly, you can think that C prime is like the cone of U, the genuine cone, and C prime should be R isomorphic to our original object C. And moreover, when you map things back to A, there is the right inverse, C here, that identifies things, okay? And the right inverse, the right inverse is here. And if you want really a more intuitive way to look at it, well, a triangle is called the triangle of weight R. If when you take the iterated cone from A to B to C, whatever this means, you get something which is not just acyclic, it's R-acyclic. Now, of course, this doesn't have a meaning as written here. In order to have an iterated cone, you need to have a map between the cone from A to B and C. And this is exactly what phi and psi give you. Okay, so that's the definition. So, right, let's move on. And with these definitions, you now go and check what properties of triangulated categories or what axioms are satisfied in the weighted sense. So the first thing that you check is the rotation. So you take a triangle of weight R that you see here, an exact triangle of weight R, and you rotate it, but for some reason that I will explain a bit later, you get disappointed. The rotation does not preserve the weight. So of course you can rotate the diagram, but it's not a priori true. It's not visible and probably not true in general that the rotated triangle has the same, is an exact triangle of the same weight. So, but what you can still prove is that when you rotate the triangle, so far until here is the original diagram starting from B. And now, of course, you can go to the shift of B by using the same map U or you know, like the map U. And now you include things into the further shift of B. So this means that you now in total shift by 2R, and you get here. So you get a triangle of weight 2R. You have also the octahedral property, but with weights. So I will explain this in this type of diagram. So suppose you have one triangle of weight R here, and another triangle like this of weight S. Okay, so the first triangle, you see it here. And the second triangle is here. So the octahedral axiom basically tells you that you can complete these two triangles into this huge diagram here. So you have U and V, and here you have, here I put the identity map. So here you have V composed U, and then you complete it into this purple exact triangle, and so on and so forth. What you can prove as a consequence of all this is that if the first triangle had weight R and the second triangle had weight S, then the third triangle, maybe I'll do it in this color. So there are two new triangles here, the purple one that has weight 0 and this blue one here. And this one will have weight R plus S. So I've written it here. Okay, so these things can be proved, so abstractly. And one of the things I would like to explain is how come the rotation doesn't preserve weights? So there are reasons for that. I will go briefly on them algebraically. The reasons is the following, that the notion of R isomorphism comes with a right R inverse. So this right R inverse is also a weighted isomorphism, but it turns out when you look at the definitions that you cannot prove that it is an R isomorphism itself. It turns out to be only a 2R isomorphism. And this follows from the following very, very basic fact that you can already check on chain complexes, that if you have an exact triangle in C0 with two edges, X and Y being R acyclic, then the third object is also acyclic, but it's only 2R acyclic. So you can easily check this with mapping cones on filtered chain complexes and see that somehow you cannot, the weight of that acyclicity is not preserved. It just goes up. In general, if you have here R acyclic, S acyclic, here you'll have R plus S acyclic. Okay, so I think that by now we had enough algebra, and if you feel lost because it was too many definitions and notation and things like that, I'm now going to reconstruct everything from geometry, and in a way that should be more intuitive, and in a way that should explain the seemingly looking bizarre set of properties and definitions and axioms. So how to guess all this and from geometry? So the setting in which I'm going to work is of a Liouville manifold with a fixed primitive lambda here. And I'm going to look at exact Lagrangians. The exact Lagrangians, they will already be endowed in advance, each of them with a primitive function. So it's a function on the Lagrangian whose differential is just a restriction of the Liouville form to the Lagrangian. And I will omit this function from the notation, but it is always there, always. So the underlying Lagrangian can appear many times with a function or shifts of that function. And then we have the action functional and so on. And well, the action functional if you don't use any Hamiltonian perturbations, assumes the following simple expression at an intersection point between the two Lagrangians. Well, it is the first primitive function at the point x minus the second primitive function at the point x. And we all know the Floer complex, and the Floer complex becomes a filtered chain complex by action. So if you have here you see a holomorphic strip between x and y with boundaries on L0 and L1. And you see that the action, well, it's a easy calculation that the action at the point y is smaller than the action at the point x. And therefore the differential preserves it. And you can go on, you can do a filtered Fukaya category, which is an A-infinity category. And this means that the higher operations in the category, they preserve the filtration. And you can form all the constructions that we talked about before, mapping cones and things like that. You can do in the filtered sense, and you can look at A-infinity modules, filtered A-infinity modules over the Fukaya category, etc. So at this very moment, I'm basically lying about some technicalities that I will discuss a bit later. So making the Fukaya category really be a filtered A-infinity category is not that obvious. Now I see. Yes, it's working. Okay, let's remind something about Lagrangian cobordism. So Lagrangian cobordisms are just Lagrangian submanifolds of R2 times our original manifold W. And I'm gonna endo this R2 times W with the following Liouville form. I'm gonna take the original Liouville form lambda, and I'm gonna add this term x dy. Like this is a primitive for the standard symplectic structure on R2. So V should be, in this talk, an exact Lagrangian in R2 times W, exact with respect to this, which is cylindrical at plus minus infinity. What does this mean? It means that, you know, what you see in this picture here is the projection to R2 of the Lagrangian V, of the cobordism. And you see that between x equals minus r and x equal plus r, you have something, some set. But outside of this infinite strip, things look very, very controlled. So when you look at V, how it looks over this region here, well, it's gonna look like a union of rays, negative rays here, each of them multiplied by a Lagrangian inside W. L1 array times L2 until array times LR. So it's an infinite ray. These Lagrangians are not compact. And the same thing happens on this side, right? So you have these rays that I put here, and each of them is multiplied by a Lagrangian in W. Okay, and obviously these Lagrangians in W, the Li's and the Kj's, they are exact, and they inherit a primitive function from the primitive function of V. Now, because this Liouville form x dy vanishes along horizontal rays, right? Because we have here dy. This primitive form, so it doesn't matter where you catch the Lagrangian along the ray, you're gonna get the same primitive on the Lagrangian inside the fiber, inside W. Okay, so these are cobordisms. And one thing that was realized a long time ago is that cobordisms, they give exact triangles in the derived Fukaya category, and this goes back to a work of Octave Cordia and myself. So basically, if you have a cobordism with 3 ends, like you see here, then, and the ends are K and L0 and L1, then it turns out that in the Fukaya category of W, the Lagrangian L1 there's a map from it to the object L0. And when you take the cone of this, you get something which is isomorphic to K. So you get an exact triangle. So just to remind how to make sense of this. So when I write L here and a map between L and another L, I really mean the following, that there's the so-called Yoneda embedding. So it takes the Fukaya category of W and embeds it into modules over the Fukaya category. So the embedding is basically an infinity enhancement of what is written here. So you take an object K and the module associated to it is the functor or the thing that eats a variable Lagrangian and spits out the chain complex CF of that variable comma K. So, and therefore each time you see here L1 and L0, it really means they're Yoneda modules. And why is it so that you get a cone? So let me remind you or tell you in case you have not seen this. So you take the cobordism, original cobordism here, is depicted in this picture here. And you take this curve that you see here, this curve gamma, and you multiply it by a Lagrangian X. So, and now you look at the chain, the Floer complex of gamma times X comma V. And basically what you see out of this is that this chain complex, well, as a vector space, it is a direct sum of the chain complex that you see at this point and at this point. However, the differential does not split. The differential is composed of differentials lying over this intersection point, differential lying inside the fiber at this intersection point, plus some count of strips, and maybe I'm going to erase a little bit here, some count of strips that you see here that go from this intersection point to this intersection point. And this count of strips, so you need to prove that these are all the contributions. And this count of strips is exactly the map U, and you get the mapping cone. At the same time, you can take this curve gamma times X and translate it in the plane to look like gamma prime times X. And now the Floer complex of the second one here, it's obviously all concentrated above this point in the fiber. You get the chain complex of X comma K. But this translation, that's a general invariance property of Floer homology. This translation will give you chain homotopic, homotopically equivalent chain complexes. So you get a quasi-isomorphism here. And this is why this cone equals K. So this is why you get this here, okay? And if you have cobordisms with many ends, you get iterated cones. So it's a generalization of this picture. So let's now be very, very unprecise and just think very intuitively. How should we geometrically think about a map between two Lagrangians in the category, in the Fukaya category? So traditionally, a map, well, I mean, the definition is that a map between, a morphism between these two things is just a chain in the Floer chain complex between L prime and L double prime. And for all sorts of purposes, sometimes it's good to look only at cycles. Another point of view is that you look at the Yoneda embedding, and now you have modules L prime and L double prime, and you look at the homomorphism of modules between L prime and L double prime. Both ways to look at it are pretty much algebraic. Let's see, maybe cobordisms tell us, give us a hint of look at it in a different way. So I'm going to think here about a Lagrangian cobordism V that has L prime and L double prime as two consecutive ends. So once I have such, and there are many other ends that I didn't even give them names. So once you have such a thing, well, you can look at this light blue curve gamma multiplied by any variable x. And again, as we had before, maybe I'm going to make this a bit thinner. As we had before, you can look at the holomorphic strips going from the first red point to the second red point. Right, so you have these strips here that are now orange. And this will give you really a map between the Yoneda module of L prime and L double prime. So really one way, which is going to be useful for our talk to think about a map between two Lagrangians, is to think that we have a cobordism with these two Lagrangians being two consecutive ends of the cobordism. And the cobordism will provide you already with the map. Now, the first equivalence between chains L prime, L double prime, what you see here, let me switch back to this color. What you see here, this equivalence is not really true. It's only homologically true, and this is called the Yoneda lemma. This equivalence is far from being true. However, you can make it rigorous if you throw into the picture immersed Lagrangians and immersed cobordisms, and this appeared in a recent paper of Kone and myself, where we developed this formalism. But we are now on a very intuitive level. So let's pretend that everything works. And also, I don't want to deal here too much with positive and negative ends. And this is always possible to bend the ends and make all the ends be negative, like you see here. Okay, so we will do that. So if we accept this as something to, to play with and guess all sorts of properties and constructions from, you cannot resist but admit that we are actually not using all the information from this picture. So you see, this picture carries out a numerical measurement, which is called the shade of the cobordism. So what is the shade? Sorry, the shadow of the cobordism. So what is the shadow of the cobordism? The shadow of the cobordism is basically the area of the projection to the plane. So not quite, you project the cobordism to the plane, and if there are holes inside the, this bulb here, you fill them in and then take the area. So formally you project it and you add the bounded connected components of the complement of the projection, and now you take the area. So the term was coined by Kone and Sheluchin, where they studied this shadow in case you have cobordism with exactly two ends. And in another paper with Kone and Sheluchin, we studied this shadow in the context of many ends and constructed all sorts of metrics out of it. We will get to this a bit later. Okay, so let's put the actions into the story. So how should we think geometrically of an R isomorphism? So first of all, once you see isomorphism, this immediately should tell you that maybe you should look at cobordism only with two ends. Of course, this is not precise what I'm saying, but this is like a good intuition for the story. So let's look at a cobordism with two ends, and this like this, end A and end B. And let's take here this vertical line is at x equals 0. So if you now look at the strips that go from the upper red point to the lower red point and count them, you get a map U from the Yoneda module of A to the Yoneda module of B. And it's quite obvious that the cone of this map U is going to be R acyclic. What is R? R is exactly, it's not the shadow of the cobordism, it's the shadow of the cobordism plus the other part lying between the vertical line and this part. So it's like this S that you see here. Why is this R acyclic? Well, just because you can take this vertical line here and translate it to the left and disjoin the cobordism from the vertical line. And the Hofer energy you need in order to achieve this is exactly R. And standard Floer theory will tell you that you get an R-acyclic object. So this is how I'm going to think R acyclics. So a cobordism with two ends will give me a map, U, and U is going to be, and the cone of U, not R acyclic, R isomorphism. And U is going to be an R isomorphism if its cone is R acyclic, and this is how I think about it. Here's an example where there's no bulb. If you take our inclusion inside the shift map, eta R, and its cone, you get this picture, and this is definitely an R isomorphism. Let's now try to understand weighted triangles. So there was a very complicated definition for weighted triangles. Let's try to understand them from the point of view of cobordisms. So remember, a weighted triangle was a diagram. A goes to B, goes to C, goes to the shift minus R of A. And we want to say that this is exact of weight R. So again, let's take here a cobordism V with three ends, A, B, and C. And let's take again this vertical line. And again, if you count strips here, you're gonna get the map, one map from A to B. And you count strips here, you get another map from B to C. And let's pretend that this is general enough in order to insert them as our maps to be considered in a triangle here. Okay. Now, if you take this end C and bend it the way I depicted here, you bend it like that, and you check what happens to the primitive functions, you see that you get exactly the shift of C by R units, where R is the shadow. So I'm cheating a little bit. You get a bit more than that because there is this, gray area here that you cover. But obviously you can make this gray area to be as small as you like. So that's a good approximation, okay? And this thing itself comes with a map here. So let me get rid of the gray area. So this itself comes with a map here, W, that is going to count strips that go from the upper intersection point, might fill all this thing, and then end up here. So maybe it's a good moment to use the pen and not the highlighter. You see, from here, maybe not, maybe in black, it's better. From here to here. And you get the map W. And the map W is from the shift by R of C to A, or equivalently from C to the negative shift of A. Okay. So how is this related to the formal definition of weighted triangle I gave earlier? Well, you can see in each of these pictures. So here you have the formal definition. Here you have the formal definition. And in the left picture, you can see in green the cone of the map U. The cone of the map U is what we called in the definition C prime, and you can see it here. And the cone of U comes with a map to the object C, to the module C. Well, you count the strips going from the upper green intersection point to the red one, as well as from the lower intersection point to the red one. So this is the map phi. And the map C is defined in an analogous way, as you see here. And it's a kind of, looking at one parametric family of strips, and compactness and gluing will basically show you that when you compose phi and psi, you get something which is chain homotopic to eta R, and the chain homotopy preserve filtration, okay? With respect to the shift of C and C, which means that if you go back to C and C, it shifts filtration by not more than R. Okay, so let's now talk a little bit about, so this is how you should arrive to the definition of exact triangle of weight R, exactly from these diagrams. And translate it to general algebra like that. So now comes the question, how come our rotation didn't work? Well, it worked, but it increased the weight from R to 2R, right? So we had here a triangle of weight R. We rotated it. So here I used a slightly different rotation than in the what discussed earlier. So rotation clockwise, not anti-clockwise, and you see here you have sigma RC, and here you have sigma minus RC. So this is weight 2R. But you look at the picture, and we just said that the weight is basically the shadow. And you take this cobordism here, and you twist, you bend the C end above it. You indeed get this object here. But the shadow doesn't change, it's the same. So how come the algebra misses that? And there is an explanation to it, and I'm gonna briefly explain it. So how do you actually understand this rotation algebraically? So I'm gonna do it geometrically, but each of these steps translates to algebra perfectly. So you start with the left picture here. And in the left picture, well, what you see here is what I can think of as an iterated cone between A, B, and C. You see you have these maps between A and B, and from B to C, and from A to C. So you get an iterated cone, and I'm gonna call the chain complex coming from this by K. Here you have the tautological one that comes from taking the cone of eta R. I'm going to call it K prime. And here you have a complicated one, which is what? Well, you take you take the cobordism V from the beginning. Now you start bending the C arm, but you don't bend it too early. You first cross this vertical line, then you bend it, go all to the right, and then up and above the cobordism until you get here. Well, then you get a chain complex that has, it's a direct sum. Well, the underlying vector space is a direct sum of 5 components, right? And you have here, and if you look, you see that what you get there is really the cone between the cone of eta R and K. And you get here a triangle, K prime, K double prime, and both K and K prime are acyclic. You see this from the picture, and therefore K double prime is 2R acyclic. But geometrically, it's really R acyclic. It's not 2R acyclic. So why? So here you see that the algebra needs more input. So if you have a chain map between 2 chain complexes, both of them being, null homotopic, so K prime and K double prime, you look at the cone between them. And suppose that the first one has a homotopy, a chain homotopy, that makes it null homotopic, which is H prime. And the second one is done by a chain homotopy H. If you know that the chain homotopies H and H prime are correlated one to the other, then, they are compatible with a map F in the sense that this diagram commutes, then they fit together to one chain homotopy that will make the cone of F acyclic. And if you look at the formulas, you immediately see that if H and H prime both shift filtration by not more than R, the new one for the cone will also shift by not more than R. And if you now stare at this geometric picture, you immediately see that in geometry this happens, because in order to make this chain complex, this K acyclic, all you need to do is translate the vertical thing to the right R units. And the same, very same Hamiltonian isotopy will also make disjoin, the vertical line with V prime. And so you get such a diagram, and this is really the reason why you get here in the rotation the same weight R, and not 2 times R. So that's the reason, and
Paul,
it's not clear to me how to formalize this in persistence categorical terms. You probably need to go to some more sophisticated structure like infinity categories and things like that, because persistence category will not encode which homotopy was responsible for making something acyclic.
Paul?
Yes, we need to finish, I think.
Yes, but
okay.
You can, by tradition, can take another few minutes for sure.
Okay, I don't need much. There is a geometric view on the weighted octaedral axiom, and I'm just gonna show you the picture. So this very frightening diagram that is hard to chase basically can be understood in the level of drawing cobordism diagrams in the plane. So you have this, what you see here is the way we were thinking about a morphism U between B and C. What you see here is a morphism between C and D. And now you have this C and this C here. You bend this end and you glue them. So now you get a much larger cobordism with 4 ends. And in this cobordism with 4 ends, we have end B, D, E, and you see I also bent here A, so you get the negative shift of A. And now you go and you take this curve here, this dotted curve, times X, and you look at what does it calculate for you. You'll see that you get here exactly the mapping cone of the composition, the composition between the maps sigma and tau that appear here, the one that goes from E to C and then from C to A. At the same time, you can also take the same cobordism and compare it with this dotted curve. And when you compare it with this dotted curve, you easily see that what you do here is basically the cone of V composed with U. You see here U, and here with V. On the way, you have a very nice interpretation here of the construction called mapping cylinder. And this comes by taking these little parts here. And now you stare at the 2 dotted curves and you see that they are basically Hamiltonian isotopic. And therefore, this cone and the other cone are the same. Well, they are isomorphic. And how much energy you need to go from one to the other? Obviously, you need energy R plus S, right? So you see this dotted thing is under the 2 bulbs, and this is above them. So you need R plus S. And I don't know why. Okay. So I'll be very brief here. You can look at iterated cone decompositions in a triangulated category. Sorry, in a persistence triangulated category. So you have an object X, and you can attempt to build it as a cone, by iterated cone, by attaching more and more objects from a list of objects x0 until xl. And this is done by these triangles here that you see here. Okay, so we don't use the word cone, but we have a triangulated structure. So you have all these triangles. You start with a given object, x0, and you end up with the object that you wanted, x. And each of these triangles might have a weight, and the weight, the total weight is the sum of the weights. And basically all this octaedral axiom, not axiom, property, the weighted one, tells you that if you do cone refinement, so you take an object and have a cone decomposition for it, with objects x0 until xl, and then you take xi here in the middle. Sorry, you take xi here, and you decompose xi by some objects z. Then you get, of course, a longer cone decomposition, like it's written here. And the weight of the longer one is not more than the sum of the weights of the original ones. Okay, so it is sub-additive in this respect. Okay, and of course, for all this to make sense, you cannot really work with the category C. You need to work with the category C infinity, which, as I explained, it has the same objects as C, but the homes are just the limits, the direct limits of the persistence homes here. And what it turns out is that on C infinity, you have a honest to go triangulated structure, and you can easily guess what it is. Well, a triangle here is going to be distinguished if it lifts in the past, right, to some finite R to a triangle of some weight R. And once you work in this setting, everything written here really makes sense. So to finish the story here, so here's a measurement that you can do. You fix a collection of objects here, and you assume that these objects generate your category C infinity in the triangulated sense. And now you go and measure how much weight do you need in order to generate the object X. And so this is called rho XF. So it's the infimum of the weights, where it is a cone decomposition with objects only from the family F. And you take the weight of this. And okay, so if you work with chain complexes, such a notion has already been considered in our paper with Kornia and Sheluchin, where you try to infamize the boundary depth of a left homotopy inverse of a given map. And the very same principle can be used in order to measure split generation. You just don't require here an isomorphism. You just require that you have a map and you have a left homotopy inverse. So this works as well. In the cobordism category, you can do the same measurement only by taking shadows. And so these are all non-equivalent things, but they come from the same underlying idea. Right, so, okay, I will skip this. It's possible to apply this to some things in cotangent bundles, but the last thing I wanted to mention is that there is a work of from about 10 years ago of Abu Zaid about split generation of Fukaya categories. So inside this work, there is an algebraic criterion for a family of objects to split generate a given object. And this is a purely algebraic criterion, which is related geometrically with some open closed and closed open maps in symplectic homology. It seems that this criterion can work also in the filtered case. And it seems that you can talk about weighted split generation and find really a very precise criterion that resembles exactly what Abu Zaid did. So unfortunately, I don't have time to explain this. So maybe I should end the lecture now. I'm over time anyway. So thank you very much.
Thank you, Paul. So
I'd like to open the video here so that I can see you. Yes.
Right. So let's see if there are any questions.
I have a small question. The G prime and G2 prime, which appear in the associated with R isomorphism, are stably equal or not? I mean the composing eta r, they are equal or not.
I'm sorry, I'm not sure I understand B and B prime.
G and G prime, G prime and G2 prime, which associated with R isomorphism.
You are talking about the right inverses?
Yes.
Let's try to find them. It was a long time ago.
Yes.
So what is the question about them? Not here. So what was the question about them?
G prime and G2 prime are stably equal.
Yeah, they are equal if you push them to the future. By R. This is
by
what
R, yes, yes. I see. Yeah. So actually they defines isomorphism in C infinity. Right?
Well, if you push after the correct pushes, the things will become isomorphic in C0 for some shifted objects.
I see.
Yes.
Thank you.
For some reason, I could not find where the definition was probably. I don't know where it is. Okay. Any other questions here? Here it is.
So let's see if there are any other questions. Okay, if there are no more questions, we're just gonna thank Paul. Thanks again, Paul. Of course, we can ask questions after, but I mean, it's not. Okay, so maybe yeah. So this algebra part is there's a lot of algebra in this. So maybe I'll ask a question because you wanted to say something about the splitting, this Abuzaid and Ganatra point at the very end. Maybe you can say a few more words about that.
Okay. So the story there, I need to to get there somehow. Maybe that's the best way. Right. So the story there is the following. So you have an infinity category, and do you see the screen? Or?
Yeah.
You have an infinity category, and you have an object. Sorry, a family of objects that split generate the category. And sorry, you have a collection of objects, and now you ask if a given object, let's call it K, is split generated by them. So split generated means that you can find an iterated cone with objects from B that will contain K as a direct sum inside them. And there's a way to do it. There's an algebraic criterion. You take the right Yoneda module of K here, and the left Yoneda module of K. So you have two modules, left and right modules over the infinity category B, and you can tensor product over B, and you get a huge chain complex that looks like the bar chain complex. So it's written here, the chain complex. All the higher operation mu are involved in it. And now there is an obvious evaluation map from this chain complex to the endomorphisms of K by applying all the higher compositions. And turns out that if the unit here in homology is in the image, then K is split generated by the family. And you can do everything here, everything in a filtered setting. So if the category is filtered, you can take this tensor product, and it's going to be a filter chain complex. And now, okay, you have two filter chain complexes and this evaluation map between them. And what kind of numerical invariant can you cook out of it? Well, you can take the cone of this, which is acyclic. It's acyclic by a result of Ganatra. And you can take the boundary depth. And my feeling is, so I have not checked all details, is that the split generation distance or measurement for K is bounded above by this beta, by this map, this boundary depth of the mapping cone. This should have a quantitative geometric counterpart by looking at the open closed and closed open maps from the Hochschule homology. So everything here should be filtered. Only that you see, I ended here the talk with a citation of great personalities of our times. This might be all fake news because, like I said, all these Fukaya categories are they are not really filtered; they are weakly filtered. There are errors in the preservance of the filtration in the higher operations, and consequently, the Hochschild chain complex is not really filtered. So one needs to settle this problem. But at least on a very intuitive level, this is what should hold.
All right. So thank you very much again, Paul. And